Today I will talk about the problem which is proposed by Bertrand. The problem proposed in the 1889. The problem name is Bertrand Chords. In the statement of the question it's written like that: a chord is randomly chosen on a circle. Calculate the probability that a chord is longer than the side of any equilateral triangle inscribed inside the circle. There is almost a seven approach to this question, but three of them described very well, and I am going to talk about the three of them and going to explain the paradox of this three answer and going to explain at the end the final answer of this question. One of the approaches named random endpoint approach. In this approach, one endpoint from A, for example here, chosen from the circle, and we draw many charts from these endpoints. Like, as you see, there can be infinite charts can be drawn from this endpoint. And if endpoint goes to AB, the side AB, I mean here, and side AC here, AC arcs chords will shorter than side of the triangle. But if width chords go from A to BC, these sides, as you see, it is longer than the side of equilateral triangle. So we know that in this circle we have three equal arcs is equal to 120 degree because the triangle is equilateral. I mean these are 120 degree, all of this. Yes. When calculating the probability with this approach, it will be same for all points. For calculating the probability, we must divide 120 by 300 to 360, and at the end we got 1/3 as answer in this approach. It is the first approach I explained. Now passing to the second approach, which is most I liked and most I understand. In the second approach, one radius is chosen and some chords are drawn perpendicular to the radius. I mean this. And chords which are above the side of the triangle BC are longer than side. And from the geometry, we know that this part is longer than this part twice, because this line is median, and in intersection point line is divided by 1 and 2 ratio. So we can say that line which is below also equal to r divided by 2. These are the same. It is according to the geometry. So we can, for calculation the probability, we need to divide the r by 2 and divide the answer by r, and at the end we get 1/2, which is different from the first approach. Now in the third approach, circle is drawn inside of the triangle. As you see, chords which midpoints are inscribed the circle of the triangle are longer than side of the triangle. For calculation, we have to divide the area of this inscribed circle by the outside circle. According to the geometry, radius of the inscribed circle is shorter than outside circle. I mean the radius of this inscribed shorter than the outside circle as twice. It is according to the geometry. For equilateral triangle, if it is inside, if it has equilateral triangle inside of the circle. And so area of inscribed circle is shorter than outside circle as 4 times. As you know, area of this is shorter than outside circle as 4 times. At the end, we divide inscribed circle by outside circle and got 1/4. Now actually there are 4 more solutions for this problem, which all the answers are different from each other, and it is making the paradox. And Bertrand's third problem shows us the limitation of the classical probability when applied to the problem where the number of possible outcomes is infinite. What what it is mean here? I mean, you can draw infinite number of the sorts here, and you cannot approach the problem which the outcome is infinite. And in 1912, the Painter adduced a new method to solve the problem where the number of possible outcomes is infinite. This method is integration method. He suggests the probability density to eliminate the interpretation of the randomness. So it is always that if we can find the probability density for the random variables, we will get the same answer. We will get the answer. One important remark is the probability density exists only the random radius approach. Now we get he proposed the integral like this, where the C is a small concrete circle, fxy is the coordinate of the midpoint of the chord relative to the center of circle. 8xy is the coordinates of midpoint of chords relative to the center of inscribed circle. Rotational invariance implied that both fxy and 8xy depend on xy only through the rational distance x squared plus y squared. Therefore, in the polar coordinate theta, the above the equation becomes like this. And in this equation, it is going to be integrated. But as you see, it is not easy to integrate this function. Here he is calculating the integral. For calculating the integral, he is finding, as you see, at the end, for the calculation, he is using the different differentiation methodology to simplify the equation. At the end, he got the integral like this, and also tried to solve this equation to finding the differentiation of this integral. See, his way is a is constant, and he is differentiating, and at the end got the answer like that. And then he got the integral like that. I also tried to solve this integral, and I got the answer the same as he got. And the equation described is this equation below, as you see, is described in this general solution for what he got from the differentiation. Now, remember this equation. A transitional invariance, he applied transition invariance implies where true is a constant and equal to 1. We got this simple equation where R is greater or equal to 0 and less than or equal bigger, and also theta greater or equal 0 and less than or equal to p. And by this equation, at the first, when we start the integration, we have this, but he simplified this and get this equation, and simple integration method, he solved it and got 1/2, and he concluded his solution. Now I want to say the one thing. So explanation of equation finished. However, in 27, Shackle published the paper casting some doubts on Jane's solution, and he says that the problem still remains unsolved. Thank you for watching my video. Thank you so much.